Last time we learned how to use experiments to test moderation and mediation. This time we learn how to design correlational studies that test mediation and moderation. Correlational studies are just measurement studies, not manipulations. So even when you measure categories like race, you're using correlational methods. But before we do that, I need you to define mediation and moderation and make your own memes for each. This is entry ticket 1 and 2. Now pause the video until you are done. Today, our goals are to learn how to set up correlational designs that test mediation and moderation. The most important thing we're going to learn is that the temporal sequence, the order in which you measure things, matters a ton. Correlational designs are simple. You measure a bunch of things all at the same time in one study. However, people can't actually complete 2 measures at the same time, so you have to choose the order. Your basic correlational design is pretty simple. You measure 2 things at roughly the same time, like measure apples and oranges, and see if they have a relationship. We've all heard that correlation is not causation, which is true, but it is also the most frustrating sentence that Dr. D hears all the time from students. Sometimes you can use logic to assume causation from a correlation. As one ages, their income increases. It's impossible that one's income causes one to age, so we know the direction of that relationship. So we know that age causes income to increase, likely due to some mediators like time on the job or even having a job. Likewise, we know that political attitudes are correlated with the year one is born in. If you change your political attitudes, you don't change the year you were born in. Your age is likely causing changes in political attitudes due to some other mediators like changing cultural values and norms. Or, one of my favorite, there's some research showing that for cis-het relationships, women tend to report greater attraction to taller men. It's unlikely that a sudden increase in sexual attraction for a cis-het man causes him to grow taller. Ludicrous, I say ludicrous. I think you get my point. Sometimes logic allows you to deduce causation. Because, remember, for every correlation there is a cause to be found. But then sometimes logic can't save you. Happiness is correlated with income. Does income cause one to be happier? Maybe. Or do happy people make more money because they're better coworkers? I don't know. See, sometimes correlation is not causation. In this case, there is no logical way to deduce the relationship. However, the true fact is that when anyone runs a correlational study, they choose one variable to be the independent variable and another to be the dependent variable. Sometimes they use logic, like we just reasoned for some examples. Sometimes they use past research. Sometimes they use their research interests. If you're a happiness researcher, happiness is your dependent variable because you care more about happiness. Generally, if you research something, that is your DV. I study racism. I often measure racism as my dependent variable. Now, if you were an economist, money is going to be your DV, and you're going to flip the relationship that we see here. Sometimes you acknowledge that the directionality could go either or both ways. But even if you can't decide on the directionality of the relationship, you still choose one to help you make your models and answer your questions. Like when you do a data analysis, you eventually have to choose which one is the independent variable and which one is the dependent variable. If I don't tell you which is which in a problem, and the causal relationship is not logically apparent, like height and attraction, you can choose. But ultimately, you measure the independent variable first, and you measure the dependent variable second. So let's complicate what I just said. So whenever you see a moderation experiment, the order of measures by itself will tell you which variable the experimenter thought was the IV, the mediator, and the dependent variable. So essentially, you measure the independent variable first, the moderating variable second, and the dependent variable third. This leaves us to our third entry ticket. In a test of moderation, all you know is that I measure participant race, then I measured experience discrimination, then I measure happiness. Draw the moderation model that my method suggests. Now you have to go back and look at how we draw a moderation model with the arrows. Now stop this video and get that one correct. Now, I like to complicate things if you really do not have any idea what the IV, DV, and moderator are. You don't have to choose if you randomly choose the order participants complete the 3 questions. That is, some participants complete variable 1 first, some complete variable 1 second, some complete variable 1 third, some complete variable 2 first, second, and third, variable 3 first, second, and third. This is often called counterbalancing, or sometimes it's just stated as the order of measures was randomly determined. Now that's computer coding stuff. They don't exactly mean the same thing. Allowing a computer to randomly determine the order, it will randomly do that for every single participant, and sometimes it can have, participants in unbalanced orders. Okay, so sometimes that's a bad thing. Counterbalance means you're making sure that, an equal proportion of your participants are completing all the different possible orders, which I'm not going to go through for the three different variables here. Okay. But when I do this, either way, I use computers to help me. That's why the computer's on the screen. So if you don't want to make a directional prediction and you still kind of want to test mediation and moderation hypotheses, it's going to be kind of hard, but you can use computers to randomly assign and counterbalance the order that participants complete the different measures in. Now, eventually I will show you the math. We use this fun statistical analysis called multiple regression. Multiple regression gives you statistics on something it calls the interaction term. The interaction is a test of moderation in a correlational study, so significant interaction term indicates significant moderation. Moderation and interaction are synonyms. Don't worry yet, I'll show you some math in the next unit, but I wanted you to know of this synonym toast crunch. All mediational models are causal models. You were saying that the IV caused changes in the mediator that caused changes in the dependent variable. When designing your study, you measure the IV first, the mediator second, and the dependent variable third. This assumes that, at least in terms of measuring, you're measuring them in the right temporal or time sequence. Now, you do have to think about what's logically possible and impossible. Remember, attraction cannot cause your height to change, so you have to have a logically plausible model that can happen in the order you measured your variables. Now, on to your next entry ticket number 4. I want you to get some practice designing experiments today. So I want you to observe any human behavior from your environment. So you're really trying to observe an IV and a DV in the natural environment. It can be any dependent variable, like why people drive the way they do. Maybe you notice rush hour versus non-rush hour, they drive differently. Maybe it's walk the way they do. Maybe you notice that people walk slower on school campus, but faster downtown. I sure noticed that. Act the way they do. Maybe we act differently at home than in school or in church. Just something, play the way we do. Right? Anything that you observe. You're observing some behavior in the real world and some cause of that behavior in the real world. And essentially, when you're looking at this, we know that correlations are the superior method for measuring the world in the real world. So you're looking for two things that are related in the world. Now I want you to suggest a mediator of this IV to DV relationship. And I want you to design your study for me. Okay? Just follow the prompt here and do the entry ticket. Now let's say I wanted to study the impact of race on healthcare quality, and I propose that race impacts healthcare quality because race impacts physician discrimination, which impacts healthcare quality. Right? That is, I propose that the effect of race on healthcare quality is mediated by physician discrimination. You can see this on the left. Now I would expect race to be correlated with healthcare quality. Now that is, I expect the IV to be correlated with the DV. You can see that on the right. I would expect race to be correlated with physician discrimination. I expect the IV to be correlated to the mediator. I would also expect physician discrimination to be correlated with healthcare quality. The mediator should predict the dependent variable. All of this makes sense in the causal model. I expect these relationships. Those are the 3 arrows we see right above in the model. Now, I would expect that after I control for, which is a new word that I will explain shortly, race physician discrimination will still predict healthcare quality, right? So this is what we call controlling for the independent variable. The mediator should still predict the dependent variable. However, in the final line, number 5, after I control for physician discrimination, that's the little out sign, race will no longer predict healthcare quality. So controlling for the mediator, the IV should not predict the DV. So if you look at the sort of new symbols I'm using, right, I'm putting two variables together, and I'm putting the little no sign over the variable I'm controlling for. I will explain what that means in a second, and that's okay that you don't know yet, but you will in the next slide. These are the 5 basic requirements to show mediation in a correlational study. Not everybody agrees on all 5, but when I teach this, I teach it in the simplest, most direct way. If you ever go to grad school, you will learn that some of this stuff that I'm teaching you gets more complicated, but we are at the basic level, not the complicated level. The figure on the left is a real example, and the figure on the right is the example that shows it across any different study, okay? And I hope it makes sense. If you have any questions, let me know. Now, we have not reviewed correlation too in-depthly, and it is supposed to be a review from Intro Psych. Now, I understand that not everybody covered it or not everybody understood an Intro Psych, so I'm going to go over just a little basic review. So correlation is just a mathematical value that indicates the relationship between two variables x and y. Also notice in science, x is often the independent variable and y is the dependent variable. In fact, if you think about the x and y axis, the x is where you put the independent variable, that's the horizontal, and the y is where you put the dependent variable. So that's just something to kind of burn into your brain. The sign of the correlation indicates the direction of the effect. So a positive correlation means it has x increases, y also increases, right? A positive correlation would also mean has x decreases, y also decreases. They go in the same direction. I know that's a little confusing, but don't let that worry you too much. A negative correlation means the two variables move in the opposite direction. So has x increases, y decreases, or as x decreases, y increases. The relationship between the two variables is going in a different direction. If you don't get that, we'll get it in our stats section, unit 2. Correlations range from values from -1 to 1, all right? And ultimately, correlations that are closer to -1 or +1 are stronger. So a correlation of 1 is just as strong as a correlation of -1. A correlation of -0.8 is stronger than a correlation of +0.5. I find this information to not be super important today, so don't get too stuck up on it. But what is important is the concept of R squared. So when you square a correlation and multiply it by 100, you get the percentage of similarity between the two variables. So if you ever find a correlation of 1, your x, your IV, and your y, your DV, are 100% the same exact measure. If you find a correlation of 0.5, 0.5 times 0.5 equals 0.25, times 100 equals 25%. Your two measures are 25% related and I guess 75% unrelated. That's pretty simple. It's not a massively complicated measure. Sine says the basic direction, and squaring it tells you the percentage similarity or relationship among the two variables. That is my review. If something doesn't make sense, ask me a question. Here you see a visual representation of the correlation. Right? I have a key at the top with different colors that represent the IV, the DV. The brown color represents our IV of race. The black color represents our DV of healthcare quality. To go back to our previous visuals, I want to connect the two images for you. And the gray area represents the percentage overlap among the two variables. Well, this is our correlation squared, or our R squared, and we're going to assume the correlation is 0.5. 0.5 squared is 0.25. 0.25 times 100 is 25%. Patient race is associated with 25% of healthcare quality. So this is just kind of an overview from last slide. The correlation tells us the relationship between the two variables, but to really put this in common sense terms, we square the correlation and multiply it by 100. So in this case, our two variables are 25% related. The most logical interpretation is that patient race accounts for 25% of healthcare quality. A safer way to say it, another way to say it, is that patient race is associated with 25% of healthcare quality. Or even 25% of healthcare quality is associated with patient race. I don't personally care how you say it, I just care that you get that the two variables are 25% related. We get our correlation value, we square it, we multiply 100 to get percentage relationship. More advanced statisticians, this is to prepare you for the future, more advanced statisticians will say things like race accounts for 25% of the variation or variance in healthcare quality, which is saying the same thing. Most of the time when you hear variance in statistics, you have to translate it to differences in scores. So race accounts for 25% of the differences in healthcare quality scores. Yes, variance also means standard deviation squared, but when we say variance out loud as scientists, we rarely say the word variance to mean standard deviation squared, at least not in psychology. But here you have a visual representation that illustrates what a correlation is. We can use the basic concepts of correlation to control for other variables. If you look at this graphic, we have the correlation between race and physician discrimination, and I'm using similar colors from our previous model. The middle part is the correlation, the percentage overlap, the percentage similarity, the percentage shared variance, the percentage of shared differences in scores in the data for patient race and physician discrimination, our IV and our mediator. Now, that's the gray area. The Tool Dueling Pac-Man, right? The Tool Dueling Pac-Man, you know the video game, right? The one where the Pac-Man chomps on things? You can see there are two Pac-Man, right? The one on the right and the one on the left. All right, nope. Identify the Pac-Man before you move on. The one on the left represents the effect of the independent variable race, removing the mediator, physician discrimination. So you can see I have the intersection, the correlation, that's the correlation between patient race and physician discrimination. That's represented by the gray square, right? But the Pac-Man represents the pure effect of race after we control for the effect of physician discrimination. I'm using the same symbols I used before. The Pac-Man on the right represents the effect of physician discrimination after we remove the effect of patient race. So these are the controlling for variables. Now, when you make a mediation model, you have to be rigid and absolute in your thinking. Our mediation model for this problem says that the effect of race on healthcare quality is completely caused by physician discrimination. I know you may not logically agree with this assumption, but that's what we're saying today. Remember, the first time you learn something, you don't want to overcomplicate it. You want to learn the simplest case. So I get it that things other than healthcare provider discrimination can cause racial biases in healthcare quality. But today we're going to be rigid in following the model. When we do the analyses, our analyses will allow for more flexible possibilities, but being rigid in this formulation is the only way to learn mediation well. So be a little rigid in this example. Okay, so don't fight me here. So we're saying if our model is correct, and if the effect of race on healthcare quality is completely caused by physician discrimination, then we expect the effect of race after we control for physician discrimination, that is, remove all the overlap between these two variables, should not predict healthcare quality. Race controlling for discrimination should not predict healthcare quality because we were saying that racial bias in healthcare quality is completely caused by physician discrimination. Remove the discrimination, remove the correlation. That's why I put the no sign on the arrow on the left. One way to think about this is in just reality. What is left in the race variable after we remove a control for discrimination, prejudices, biases, implicit biases, etc.? A lot of beautiful things I call culture. So our race variable removing discrimination is cultural differences across races that were not due or caused by discrimination themselves. Cultural differences are beautiful. Differences in religious belief or how we celebrate life and live life. Since we have the same bodies, I don't see why these beautiful cultural differences should lead to differences in the quality of healthcare decision making we receive when we go to the doctor. You've heard me mention this before, but I'm Polish and I eat pierogies. This shouldn't impact how my doctor treats my broken arm. He shouldn't treat my arm any different than someone who eats one of the other great cultural inventions across different cuisines. Like, if somebody eats egg rolls or empanadas or beef patties, we shouldn't be treated differently, right, by our physicians. So our beautiful cultural differences, like differences in cuisine, right, shouldn't impact how we are treated. Now, we can do the same kind of logic, but for physician discrimination. See, if physician discrimination is the cause of racial differences in healthcare quality, when we remove race from discrimination, what do we have left? We have discrimination that is not due to race, like discrimination due to sex, discrimination due to gender, discrimination due to age, discrimination due to body, discrimination due to personality. It makes sense if that my physician discriminated on me because of my gender, because of my hairstyle, or because of my age, because of my body, because of my personality, I would receive lower quality health care. So we expect physician gender discrimination or age discrimination or weight or body discrimination to lead to lower quality health care, right? So we expect that physician discrimination controlling for race, removing racial discrimination from that variable, to still predict healthcare quality, because other forms of discrimination should also impact healthcare quality. This is kind of the signature of the mediator. There are often multiple causes of the mediator. If the mediator causes changes in the DV, the source of the mediator doesn't matter. In this example, there are lots of causes of physician discrimination. Physician discrimination comes from many sources: race, gender, sex, religion, age, body, so forth. If a physician discriminates on race, this will impact healthcare quality scores. And so will all other forms of discrimination, and people can be discriminated against for many disparate aspects of their identity. The source of the discrimination doesn't matter, but when discrimination is present, for any reason, healthcare quality will be impacted. So mediators should predict the DV after controlling for the IV, but IVs should not predict the DV after controlling for the mediator. All we're saying here is that if the reason why race is associated with healthcare quality is because of physician discrimination, controlling for physician discrimination should eliminate the correlation or relationship between race and healthcare quality. However, physician discrimination, after we remove racial discrimination, we still have gender discrimination and other sex discrimination, age, body, all types of discrimination. Those forms of discrimination should still impact healthcare quality. So the effect of the mediator on the DV after we control for the IV should still be a significant relationship. And we'll get more to the statistics on that and what significance means and so forth. I know we've had a little bit of a primer on that, but ultimately, this is how we test a mediation model with correlations. We expect those 5 relationships that you should review from earlier. So, because those 5 relationships are so important, describe the pattern of data or results you would expect for your earlier entry ticket. Okay, the one where you designed your own experiment. Okay, so tell me, do you expect the IV to be correlated with the DV? Do you expect the mediator to be correlated with the DV? Do you expect the IV to be correlated with the mediator? Do you expect that the IV controlling for the mediator will be correlated with the dependent variable? Yes or no? And why does this make sense? And then finally, do we expect the mediator controlling for the IV to be correlated with the dependent variable? And also for these last 2, tell me why this makes sense. Just do your best on the why this makes sense. I want you thinking about this. It's a hard question.